Here's an example problem taken off an AP exam. This is from the AP Level B exam from 1986, problem number 3, and it seems to be somewhat related to household electricity, right? This potential difference of 120 volts is powering 3 light bulbs labeled as X, Y, and Z. Bulbs X, Y, and Z represent 3 light bulbs rated at 60 watts when they receive a potential difference of 120 volts. These are all identical light bulbs, right? Every one of them is rated 60 watts. Now that doesn't mean that they always provide 60 watts. That's their rating, right? Meaning that's the power they would get if they received a potential difference of 120 volts. Well, I think you recognize that none of these bulbs are receiving 120 volts of potential difference. Now we're simplifying the behavior of this circuit. We're treating it as if a household outlet provides DC. It behaves the same way, right? As long as we're using this RMS value, this root mean squared value of 120 volts, then the power provided by the light bulbs is the same if we treat it as if the outlet provides DC. So that's how we're going to approach this problem. Okay, so it looks like we've got this high potential here, and then there's a junction. So the electric potential, we'll call this point A, point B, point C, and point D. Actually, we don't really need both points C and D, do we? They're at the same electric potential, so I don't really need to have a point that I call C, but all these other points, A, B, and C, are all at different values of electric potential at any instant in time. So the potential difference across bulb X is the potential difference from point A to point B. The potential difference across bulb Y is the potential difference between point B and point C, which, by the way, is also the potential difference across bulb Z. You see it, right? I don't need to name this as a different electric potential. This is also the electric potential at point B, and this is also the electric potential at point C. So I think you see how we can diagram this circuit a little easier. We can say there's one bulb that's connected with one side at point A in the circuit, and then point B represents a part of the circuit that branches off, and then these other 2 bulbs are in parallel with each other, and that all connects to this low potential side. So this is my bulb X, Y, and Z. First question is, what's the resistance of each bulb? So let's see, power is current times voltage. It's current squared times resistance, and it's voltage squared divided by resistance. So power ratings are based on 120 volts. So each of these bulbs would provide 60 watts of power if the voltage was 120 volts, right? So we can use this equation, rearrange it. R is equal to V squared over P. So if they received 120 volts of potential difference, they would provide 60 watts of power. 120 squared divided by 60 gives us 240 ohms. I should say 120 volts squared divided by 60 watts gives us 240 ohms. So each of these bulbs is a 240 ohm resistor. And again, we can diagram it like this. Actually, I really feel bad about drawing this as a symbol for a battery. We'll just say at some instant in time, the potential difference is 120 volts. I say at some instant in time because we know the potential difference is oscillating. 240 ohms, 240 ohms, 240 ohms. All right. So an equivalent circuit would be a single 240 ohm resistor connected in series with the equivalent of two 240s in parallel with each other, which I think you know by now would act like 120 ohms. So we can say there's 120 volts at some instant in time that's powering an equivalent overall resistance of 360 ohms. Anyway, we found the resistance of each bulb. We've answered part A, 240 ohms. B, what's the equivalent resistance of the three bulbs when arranged in this way? So we found that, 360 ohms. Part C, what's the total power dissipation of the whole combination? Okay, so P is equal to IV is equal to I squared times R is equal to V squared over R. So let's see, we know the equivalent resistance, we know the total potential difference at this moment in time, so 120 volts squared divided by 360 ohms gives us 40 watts. So it turns out that by connecting the bulbs in this fashion, two bulbs in parallel and that combination in series with one another, would actually provide less overall light output than if just one single 240 ohm resistor bulb was connected to the source of potential difference, right? Yeah. If we take just one single 60 watt bulb, we get 60 joules of energy per second. When we connect three 60 watt bulbs in this fashion, we only get 40 joules per second of output. Okay. What's the amount of current in bulb X? So let's see. If we use Ohm's law and find the current flowing through this equivalent resistance, 120 volts divided by 360 ohms gives us 1/3 of an amp. So that 1/3 of an amp is the current through this 240 ohms of resistance, and it's the current through this equivalent 120 ohms. So if we go back to this circuit, that 1/3 of an amp is flowing through this 240 ohms, but then it splits up according to Kirchhoff's junction rule, so we get 1/6 of an amp here and 1/6 of an amp here. So what's the current in bulb X? 1/3 of an amp. What's the potential difference across bulb X? Well, Ohm's law, V equals I times R, 1/3 of an amp multiplied by 240 ohms gives us 80 volts. What's the potential difference across bulb Z? Well, we can invoke Kirchhoff's loop rule. So we say this is 0, this is 120, and then we lose 80 volts. So the electric potential here is 40. So across bulb Y is a potential difference from 40 to 0, and likewise across bulb Z is a potential difference from 40 to 0. So the potential difference is 40 volts here. Okay, we can add a final question, part G. It wasn't assigned on this exam, but we can say, what's the power consumption of each individual bulb? Let's see, now we know everything we need to know about bulb X. It has a resistance of 240 ohms. It has a current of 1/3 of an amp, and it has a potential difference across it of 80 volts. And we know everything we need to know about bulbs Y and Z. They have a resistance of 240 ohms, a current of 1/6 of an amp, and a voltage of 40 volts. So let's see. The power for bulb X is current times voltage. It's current squared times resistance. It's voltage squared divided by resistance. So we could say it's 1/3 times 80, or we could say it's 1/3 squared times 240, or we can say it's 80 squared divided by 240. Well, whichever one of those you go with, you get 26.7 watts. And you can try it. Convince yourself that all three of these give the same value. The power for bulbs Y or Z will be the same. Again, current times voltage, current squared times resistance, voltage squared divided by resistance. So we can say it's 1/6 times 40, or it's 1/6 squared times 240, or it's 40 squared divided by 240, which gives 6.7 watts. Now wait a minute, then what's the total power for the whole circuit? Well, 26.7 for bulb X plus 6.7 for bulb Y plus another 6.7 for bulb Z. Actually, what I really mean is 26.6 repeating and 6.6 repeating and again 6.6. So forgive me if I've carried some rounding off into my numerical calculations here. Anyway, if we add this all up, you know what we get. 40 watts. Same thing we found earlier in our answer to part F. Anyway, I thought that was a good example problem. See if you can find some other example problems either in your homework or from the catalog of old AP exams that involve electricity for household appliances.